Recent advances are presented in Plume-Surface interaction simulation capability for lunar landing conditions. Plume-Surface interaction, or PSI, between lander engine plumes and native regolith soil presents several primary hazards. The Marshall Fluid Dynamics branch has assembled a portfolio of simulation tools to offer a predictive capability for customers such as the Human Lander Systems and Commercial Lander Payload Services (CLEPS) landers. These tools are matured now with funding by the STMD Game Changing Development Program and the SBIR program. The mainline simulation tools are the LOCI-Chem Boltzmann Plume simulation tool and the LOCI GGFS gas granular flow solver, which directly predicts the penetration of gas flow into particle soil beds and the resulting creation of craters and ejecta streams. These tools had to be equipped with particular capabilities for the lunar environment. Plume impingement flow modeling in the lunar vacuum background requires a mixed continuum rarefied simulation capability for various plume regions, which strongly affect the resulting plume extent and impingement characteristics which drive erosion. Modeling of the liberation of soil particles are strongly affected by the extremely cohesive characteristics of the actual lunar regolith particles, which are very jagged and irregular and have a wide range of particle sizes. These capabilities have been implemented recently, and the status is presented here. On the left hand, we see the LOCI-Chem Boltzmann plume impingement modeling capability status. Within the same simulation, a switch is possible from the continuum flow solver LOCI-Chem to the LOCI Boltzmann rarefied flow solver, triggered by breakdown criteria at the cell interface. This allows a hybrid Chem-Boltzmann simulation capability, which was demonstrated recently for 3D simulations of the Apollo lunar lander impingement flow, shown in the images below. The top one shows impingement at a 5-meter elevation above the surface, and the bottom one at a 56-meter elevation. The cutting plane through the center domain shows the cell-by-cell switching between the continuum flow solver, which is shown as white cells, and to the rarefied flow solver, which is shown as blue cells. Distinct regions where the transition from the continuum to the rarefied flow solver is important, such as the outer region of the plume, shock locations, and slip flow surface areas near the impingement of the lunar soil, are clearly captured by this simulation capability. On the right-hand side, we see the current capability of the gas granular flow solver simulations. The first part of this process requires the prediction and capture of characteristics of the irregular shaped particles, which is done through discrete element model simulations of the irregular particle shapes, which are modeled by glued together spherical particles. The resulting characteristics of these simulated jagged particles are captured in a database and applied in the simulation. The current capabilities of GGFS have monodispersed particles and elongated particle capabilities, initial capabilities to perform bidisperse and eventually arbitrary polydispersed mixtures are in development, are being evaluated at this time. At the bottom, we see a simulation depicting the current capabilities. This is a plume impingement from an Apollo lunar lander at 5-meter elevation, and the resulting crater predicted with GGFS after a 2-second plume impingement on a surface of particles with 100 micron spherical particles. As was said, this capability is being extended to irregular particle simulations and polydispersed mixtures. Improvements to both of these tool sets will continue for the next 3 years of funding under this PSI GCD project, and a list of planned improvements is shown in this bottom blue box. As mentioned, this will continue for the next 3 years.